My name is Tim Montague. Welcome to SolarWorks for Illinois. Today is October 30th, and this is our monthly free webinar brought to you by Continental Electrical. Continental is an electrical contractor and solar installer here in Chicagoland. And today we are going to have a presentation by Travis Simpkins on maximizing your solar investment by adding battery energy storage. Travis is the founder and chief technology officer at muGrid, and he's a recognized expert in the design, modeling, and economic optimization of microgrids. He's currently chief technology officer at muGrid Analytics, which provides design, analysis, and economic optimization of renewable energy and energy storage projects. He has also developed a tool called Red Cloud, that is an energy optimization platform. Prior to muGrid, Travis was a senior engineer at NREL, the National Renewable Energy Lab, where he analyzed microgrids at dozens of private and public sites. Travis holds a PhD in electrical engineering and computer science from the Massachusetts Institute of Technology and a certificate of financial engineering from the MIT Sloan School of Management, as well as a BS in electrical engineering and applied physics from Case Western University. He is a senior member of the IEEE and has published numerous technical papers in a variety of fields. With that, I will let you take it away, Travis.
Thank you very much, Tim, for the great introduction. I'm certainly glad to join you at your webinar today and all of our listeners. It's very exciting for me to join you to hear about what you guys are doing in Illinois and see the great stuff going on. Although we are a Colorado company, my background, I'm originally from Ohio, and my wife and business partner is from Michigan. So certainly exciting to see what's going on in the Midwest in solar and and of course storage. So like Tim said, today we're going to talk about maximizing your solar investment by adding battery energy storage. First, a couple of words more about muGrid Analytics. Here at muGrid, we solve wicked hard problems at the intersection of energy technology and economics using math and modeling. I like to say that we operate at the intersection of how a technology works and how a technology makes money. Really, that's what we see is, what drives project development. Being able to do projects is that combination of the technology and the economic side. We are a tech and consulting company that is focused on providing bankable techno-economic analysis of renewable energy, energy storage, and microgrid projects to developers, financiers, component manufacturers, property owners, and really just about anyone else that wants to understand the bottom line of how their technology can work and how it can help them achieve their energy goals at their organization. Like Tim mentioned, we've developed our own modeling platform that we call Red Cloud. We use a lot of mathematical optimization that's really interesting and to solve some very interesting problems that we'll get to look at momentarily. To give you a couple of ideas of what we think are the key takeaways from this presentation, first, batteries can enhance the economics of a solar project with multiple revenue streams. These multiple revenue streams make optimal battery dispatching a fairly hard problem, but interesting problem to solve. And the key to economic solar plus storage is this effective dispatching. This is really what can make or break projects and getting them to pencil. So I know that there is a lot of folks that have done solar for a number of years and are getting excited about adding storage to their projects. And so I like to talk a little bit about, the mindset shift that you need to undertake as you start to get into the battery world. And so to start out, I usually say that solar is pretty straightforward. You basically can put panels on your roof, the sun shines, you make electricity, electrons flow, and you save money. It's probably a little bit more complicated than that in the end, but, relatively speaking, that's what happens. You don't really have to think about it. The sun shines and it does its thing. Batteries, on the other hand, require decisions. If I just stick a battery in a shed out back, nothing's going to happen. I'm not going to save any money. I'm not going to make any money. I have to decide when to charge that battery, when to discharge it, what sources to charge it from, and a lot of other decisions that are either going into, from some human or is getting programmed into some controller. The point is that if I don't think about it, this battery isn't actually going to do anything for me. So how do we deal with that complexity? Well, here at muGrid, we approach it with mathematical optimization. We like to say that every time there was a decision to make, there was something optimal that you should have done. Every point throughout the year, every 15-minute block of time, there is a best use for your battery. There is a best use that will get you the maximum economic return. And of course, we're never going to get perfect with that dispatching, but the closer we get to it, the better chance that our project has of penciling and achieving satisfactory economic performance. So thinking about what are these decisions, I like to start out with a battery as a bucket, because that's really what it is. A battery is a bucket that's storing charge for us, right? And so if we were thinking about a bucket, what decisions do we need to make with this bucket? Well, we should want to think about how big of a bucket we need. When do we want to fill it? When do we want to empty it? To help us think through that, we have some considerations over here, like how fast can we fill it? How fast can we empty it? How much is the bucket going to cost? How long will it last? And what would cause it to fail? Of course, the energy that we take out of it must be worth more than the energy we put in. That's probably a fairly seems obvious statement, but in reality, that's what drives all of our battery economics, is we always want to be getting more value out of it than we needed to put into to be able to charge the battery. Oh, and lastly, we should always remember that this battery is not a perfect bucket. It will leak over time due to efficiency considerations. So one of the key points that that I think is a very good takeaway for guys that are getting started in the battery space is understanding battery power versus battery energy. And this is, I will tell you, is not that will always presented that well in the media. And so first of all, power is how fast you can charge or discharge this battery, whereas capacity is how much can it store. And so if you take those, you can then end up with duration down here. That is, how long can the battery sustain its rated power output? And so if I have an 8 megawatt hour battery, and so that's the capacity, megawatt hours, and I have a 2 megawatt power converter system, some sort of bidirectional inverter there, you could say, well, I have 8 megawatt hours and I have a 2 megawatt power system, so I can sustain that 2 megawatts for 4 hours. And that then gives me a 4-hour duration for this energy storage system. So to liken this back a little bit to our bucket analogy, I'm going to ask which of these containers is more useful. Well, depending on what you want to do with them, it could be either one, right? This big barrel at the top could be very useful to you if you are on a desert island and you need a lot of capacity to store water. But if you notice, it has very small spouts. They're only a couple of inches in diameter, so you can't get the water out very fast. So if you were trying to put out a fire, even though you have a lot of energy, you have a lot of water there sitting there, you can't get at it very quickly. In that situation, you might want this smaller yellow bucket, because you can basically, even though it only has a couple of gallon of capacity, you can get access to all of that water, pretty much immediately. And that's the same thing is true in batteries, is that if I put a big capacity battery, but a smaller inverter, or a smaller C rate, I can have a lot of capacity there and is good for certain applications. But other times I may need a lot of power. And I might want this ability to discharge very quickly, even though I'm not going to be able to sustain it for a long period of time. So batteries are similar to buckets, like in that sense, is that you can't really say which one is better until you understand the application that you're trying to serve. Which takes us to energy storage applications. So depending on who you ask, there are somewhere between 7 and 13 different applications that batteries can serve. And the reason there's different numbers is that people count them different ways. So I've got this the graphic here from Rocky Mountain Institute, which published a couple of years ago this graphic that shows the different applications of batteries, kind of broken down by whether they're customer services, utility services, or at the ISO level. And so to summarize those over here at the right, in terms of more of the the common ones that you'll see, are demand charge reduction, energy arbitrage or time shifting, so being able to use energy at different periods based on what it's worth, providing ancillary services to the grid, which could include frequency response, and below that then demand response, reliability, and under reliability you might include things like energy security, resiliency, backup power, black start, and then capacity markets, and finally transmission and distribution upgrade deferral. And so while we were chatting earlier, Tim asked me, like, what's the difference between peak shaving and demand response? And I think that's an excellent question, because in some ways they are, they're two things that are happening, that are very similar. One of these is a customer side that's behind a meter, whereas a demand, that would be the peak shaving. And the demand response is really like when the utility asks you to reduce your load. And so, that's really, something to keep in mind here is that some of these you can do that might be able to happen at the same time, and other ones might not be. And that's really where we get into battery revenue stacking. So, I say here batteries can serve one application at a time, but if you're lucky, you might actually be able to get two of them, depending like if a certain event, demand response event, happened at the same time that you wanted to do your native peak shaving. But most of them, like providing frequency response, you're going to have to do separately. So serving one application may preclude it from serving other applications at the same time or in the immediate future if, for example, the state of charge of your battery ends up lower after the previous application has been served. So battery dispatch optimization is then the process of determining which applications a battery should serve and when it should serve them. And so down here at the bottom is, a very, very hypothetical, time frame of a day where you might be using a battery for doing different purposes, different applications. And so maybe overnight you're doing arbitrage. You're charging low to be able to get in position to do these others and have a full battery that's ready to to be able to serve these applications. And so, it's probably worth noting that, some of these, this is kind of future looking. That right now, I don't know of too many that are able to mix frequency regulation with peak shaving, for example. But, as we go forward, I think you're going to start to see more and more of that, where you can bid into certain markets, and then you can use your battery for other purposes during other hours of the day. So it's worth thinking about what that is, what that might look like, even though today you're still seeing lots of, probably dedicated, predominantly one application. So, moving on to, what else, what drives, if you were doing, say a peak shaving application, for example, how does it, how do you interact with utility rate tariffs? And so this is a little bit of a, it's a primer on how utilities bill for electricity. And so typically there's three different types of charges: fixed charges, energy charges, and demand charges. And so a fixed charge, looks like something that you pay, a flat amount every month, sort of just for having the privilege of, having electricity at your site, having that meter read, having that, that capability. The energy charge, of course, is what you pay per kilowatt hour. And so the solar, if you come from solar, you think a lot about energy charges, because that's really the primary one that solar is able to offset, is it's able to displace kilowatt hours at, pretty much a one-to-one basis. Every kilowatt hour that solar generates, you don't have to buy from the grid. Well, then the next one down there is demand charges. And oftentimes that's what we're looking at the most with particularly behind the meter battery installations. And so the demand charge is the maximum rate at which you use energy. So that's your peak demand. And then your utility may assess a charge per kilowatt of per month of whatever that was. And so if you look over here in the graphic over here, this site has a 1700 kilowatt peak demand, which is the maximum rate that they consumed electricity during that month. Of course, we're only showing one day here, but you know that's what the peak is. And so you can multiply that by 20 in order to calculate what their peak demand charge is. And of course, both the energy charges and these demand charges may be subject to time of use. They might be subject to lookbacks and ratchets and tiers, which all adds complexity to this and gives you more opportunity to optimize around this space. So it's a question we often get is, how prevalent are demand tariffs? How prevalent are these demand charges in the bills that organizations face? And so, you know, as consumers, from a residential perspective, we don't think too much about it because it's pretty uncommon to have a demand charge on the residential side. But when we start looking at the commercial and industrial space, you know, they're actually a lot more, you know, they're a lot more common, and they vary significantly in terms of what the maximum demand charge is. And so this graphic here by the National Renewable Energy Lab shows geographically what the peak demand charge is in each region. And so this is there's some simplification done behind the data set, which I'll mention you can go download if you're interested. But basically, this is the peak of any rate tariff in that location and what it is. And so the darker is the higher. So you can see out here in California, there's a lot of places that have some rate tariff that has a peak over $30 per kilowatt. And as you look in different parts of the country, you know, it varies. You know, some of them, there's this yellow down here at 0, and it ranges to, really, anything in between. And so I've highlighted over here because I know that we have a lot of interest, obviously, in Illinois here. What does Illinois look like? Well, there's this orange up here around Chicago that's a $1 to $10, and there is some, there's some peak down here, in the south central part of the state that's, up over 30. And so we say, well, what does that mean? And there's sort of a general rule a rule of thumb in the space that if you have a peak demand charge somewhere around $14 or $15 per kilowatt, that you might have to be in the running to have a project. And so that's not a hard and fast rule. I've seen projects that can do battery projects with demand charges down around 10, and I've seen ones that are up around 20 that, because of oftentimes the shape of the load profile, it still doesn't work there. And so, it's just a rule of thumb that, if you have a client that's, peak demand charge somewhere around 15, that it's probably worth looking at batteries. That's kind of where the threshold starts. And so, I've talked a lot about peak shaving here, and I just, I think that it's, and how it works with the load profile. And it's interesting to think about that to make it a little more concrete by thinking about mountains. And, partly we're a Colorado company, so these are, these mountains are near and dear to our hearts. They're the Colorado 14ers. And so they're 14,000 foot peaks. This is actually Mount Yale at 14,199 feet. And if we were to think about, wanting to do peak shaving, what does it mean? Well, there's this peak up here, right? And so, doing a peak shave, if you wanted to get this a little bit lower, you would push some rocks off and push them over here to the side. And oftentimes our mountains have these what are called cairns on top. And so people have built these little structures. I don't know, they're like 5 feet high, 4 or 5 feet. Sometimes there's a dugout that you can get out of the wind because it's really windy up there. And so the first thing, if you wanted to lower this peak, you would just scatter those rocks around. And you could probably save 4 or 5 feet. You could shave 4 or 5 feet off the top of this mountain. And if for some reason someone was paying you $20 for each foot, you could make $100. And I often say that, well, we joke about this, of course, but, these are the collegiate peaks. And so, there's legend has it that, Harvard has, paid students to come out once to make Mount Yale shorter so that Harvard would be taller. And so you can think about it like that if you want to. Well, so here's what the profile looks like of this. And so back to where, the discussion here, that if you were to knock this pile down, first of all, you would just knock the wee tippy top off of this, and you really didn't have to do much work for it. But as you want to go further and further and further, suddenly now you need to have shovels. And eventually you would need to have earth moving equipment. And eventually you're doing a lot of work to get every single foot off of this peak, right? And so that's kind of the same way that works with peak shaving your electrical load profile. Is the first little bit is relatively simple. You don't need a lot of energy capacity because you're not moving a lot of energy around. And so it can be very lucrative. But the further you go down, just like with the mountain, the harder it is to do that, the bigger battery it takes, because you need to move a lot more energy. And eventually, you might think that the ultimate goal is to get this flat. Well, eventually you run out of places to put the dirt. And the same thing is true in peak shaving in terms of electrical load profiles. Eventually you run out of places to shift energy. And at that point, there's not too much you can do. And so that gets us to, there's this optimal, right? There's this optimal level that you should have, that you should want to be able to do to maximize your project economics. And so like we've talked about here, you have these factors of what are the revenue streams that I want to go after? What does my load profile look like? What does the cost of these technologies? We haven't really mentioned that, but the cost of batteries has declined significantly. Where do those factor into? And so as you have these technologies, and maybe you have even more at your site, you probably already have solar. You might even have, other types of conventional generation. You might have some CHP. And so by bringing all this together, we are able to figure out what the optimal system sizing and dispatching is to maximize the net present value of this project. And that's really the goal of being able to drive the economics of these types of projects. So I think it can be useful to go through a brief case study of what this can look like. This is a case study that we've put together that's for a site that's in Los Angeles. And so this their utility down there is Southern California Edison, which is it's a progressive utility like many in California are in terms of what their rate structures look like. They have time of use. They have an electrical load profile with a interval data at 15-minute level. And so that's very useful when you're evaluating a battery energy project. There's a lot of parts of the country that don't have time of use data yet. And so you might need to put a data logger at your site. There's a variety of them out there that will record at minute level, and so you can get that data. Or your utility, of course, might have them. And I think we're going to see more and more and more of those smart meters get installed over the coming years. So the objective at this site was to analyze the site for energy storage potential and to determine the optimal battery sizing and dispatching with the applications of peak shaving and energy arbitrage, such that they could maximize the economic return of the project. And so what do we need to know? Well, we mentioned the load profile. And so this is our load profile over here that has for a week in July. You can see that this is, it's probably what you might expect for an office complex. It picks up significantly during the day. And then, there's a bottom at night to it. And so you can see each one of these is like its own little mountain that you might end up shaving. The other thing that you'll notice here is that these are what we call peaky. They're very jagged on top. And so that is actually very useful. That's a very useful load profile for batteries to operate on. If you have a load profile that's got a flat top, like we mentioned back with the mountain example earlier, it requires more energy to be able to do that. So when you see a profile like this that's pointy, has tops to it, that is something that you might want to look at for batteries. So then we have some, installed cost assumptions. We have to assume something. This is, we're assuming, $800 a kilowatt and $300 a kilowatt hour. And I make that distinction because it allows you to think about the duration that you need separately. So instead of just saying that I'm going to put in a 2-hour battery or I'm going to put in a 4-hour battery system, maybe we want to think about, well, what is the characteristics of my load profile here? The applications that I'm going to serve, and allow a model to figure this out for me mathematically. And so that's why we separate these out. And of course, you may have your own beliefs of what you can get batteries for, and that's great. You can feed that into a model directly, and have that factor in. Of course, we mentioned the available applications, and the next thing we want to talk about is the utility rates. And so, like I said, we're in SCE territory out here. This is the General Service 3 Option B, but I think this is from perhaps a year ago. So these numbers may not match up exactly today, because that's another thing, that rate tariffs change quite frequently, at least a little bit in terms of how they, the specific numbers. And so the key to this rate tariff is that it is a time of use rate. And so if it looks complicated, that's because it is a little bit. There's different rates for energy, which on here is labeled as usage, and demand. And they're different rates for different periods of the day and different seasons of the year. And so if we look over here at the summer period, we can see that this has a 14 cent per kilowatt hour usage during the afternoon hours from noon to 6 p.m. And they call that the peak period. And so you also pay a demand charge of $17.42 for the peak that happens during that period across the entire, all the days of that month. And so you have, say, probably 20 days that month, and you have 6 hours each day. And so, you have the peak of those roughly 120 hours, you're going to pay that $17.42 for. And then there's this part peak period down here that is kind of shoulder hours. And so they're the morning hours and the evening hours after that peak. And then the off peak is at night. And so the interesting aspect to SCE territory is that they then layer a monthly demand charge on top of that time of use demand charge. And so here you can see down here graphically that we've got this $17.42 per kilowatt in the peak period, but on top of that there's a $17.81 for the peak of the whole month. And so if those happen at the same time, you actually have close to a $35 per kilowatt demand charge, which, if we think back to our rule of thumb of 15, means we probably have a very good chance of a viable battery project here. So how do we think about, how do we go about actually running this, figuring out what the sizing? Well, like I mentioned, we have our Red Cloud energy optimization platform that we can feed in what these loads are, these costs, these utility costs, the capital costs of the equipment, the utility costs and the rate structure, and then the specifications of it, specifics of, how fast can we charge the battery? What is the cycle life, for example? And, there's a lot of, details of the actual equipment that you want to be mindful of. And then over here you get, well, what is my output? And so, in this case, our model found that a 1.5 hour battery actually maximizes your NPV down here, which was, in this case, about $188,000. And it breaks down, what is the demand savings? Most of this savings, first year savings, is coming from demand charge reduction. There's a little bit of energy savings, so that's the arbitrage aspect of charging the battery during off-peak periods, and then doing demand charge reduction, and as a consequence, energy time shifting during the peak period. And it's worth noting that this is a 1.5 hour battery. This is it's you could do a 2 or you could do a 4 hour battery, but to be able to drive that maximize the NPV, based on the assumptions that we put into this, we find that a 1.5 hour battery here is optimal. So then let's look at dispatching. If you remember, I said that so much of this really comes down to how you dispatch these systems. And so this is the projected dispatching that comes out of our Red Cloud model. And so over here at the in this chart, you can see that load profile, and this is now 1 day. And so you can see this, this is the shape of it. And one way or the other, you need to have this all filled in. And so mostly this is still filled in, with a gray color, meaning that you're buying electricity from the grid. But what we're doing here, and this is just a battery project, by the way, for simplicity. Obviously, you could add solar to this, and we'll show that in a moment. But this is just the battery side. The battery up here is being used for demand charge reduction. And the model finds out that this is the optimal level. This dashed line right here is the optimal amount of peak shaving that you should do. If you try to do more than that with this current size of battery, you'll run out of energy at the end of the day. And that's not good, because if you run out of energy, then before your load goes back down, you're going to end up with a demand charge there that you didn't expect, and probably all your good work that you did earlier in the day will go for naught. Another thing to note here is, that we're doing some in the part peak. And so even though this back here was only worth, $3 or $4 per kilowatt compared to the 20 right next to it, there's still benefit to being able to operate in that period. Because as you can see, we didn't have to do very much. And so even though we only got paid $3 per kilowatt for that reduction, we didn't have to work very hard to get it. And that's part of that optimization, is figuring out what I should do and when I should do it, even though it's not always obvious what those answers are. It's also worth noting here, it's over here in the bullets, that there's actually 20 different demand periods, through this 12-month time. And that's because you have a monthly for the 12 months, and then you have this peak and part peak added onto that for the 4 summer months. And so the model is simultaneously figuring out all of these 20 demand periods and the charging and the discharging that it should do for all 35,040 time steps throughout the year. So here's another day, of what's going on. You can see that, a different day, there's actually, there was more arbitrage. It just said, okay, I'm going to shave that peak, but then I'm going to discharge the battery later in the day. And so that's kind of that's kind of the beauty of using a model like this, is that it's not a canned algorithm, that I can change this strategy based on what my load is doing on different days, or what different revenue streams are available. This slide shows then, where do my savings come from? You can see that there's the green down here is that monthly demand charge. So there was $17 per month every single month. And, so there's many months it's getting the full 310 kilowatt savings on that. And then during the summer is really kind of when this battery makes, the bigger chunk of its savings, because it's also operating, it's doing a lot of peak during that peak period and the part peak period. And so you really, one of the things you see from this is you really want to have the battery operating during June through September. If for some reason you had to take this offline, or something happens, those months would not be the time to do it, because there's a lot of savings to be had. Maybe you want to aim for one of these shoulder months, when there's different, different amounts to be saved. So, we then ran a case 2 here just to, transition to, show the difference. How does it change based on if I were to put a 4-hour system? Because depending on what vendor you look at, you may only have a 4-hour system, and so you could be locked into that. Well, you can see that down here, you in the demand charge row, you do get more demand charge savings. So putting in a 4-hour battery versus a 1.5-hour battery is definitely going to save you more money. It costs a lot more. So the cost of this is, roughly twice as much to get a 4-hour battery versus a 2-hour battery. But the savings isn't twice as much. And so that's what pulled down the IRR and the NPV. Now, don't get me wrong. I mean, a 15% IRR, you should still be able to do this project. But you might have left money on the table by not being able to optimize and get the right size battery for the application and the rate tariff, the load profile and the prevailing rate tariff. Just something to keep in mind. So if we compare those dispatches, what does the 1.5 hour versus the 4 hour look like? This shows graphically what I just said, that you get more, you're going to do more peak shade. You're going to get more reduction. You're going to pull that peak lower, but you can see now that there's more red there. So as you bring that dashed line lower and lower, you're going the entire width of that. Whereas over here on the left side, in the case one, you can see that the model kind of found that I really want to stop once I get to the edge of these jagged points. Once I go any further, now I need a lot more energy. And so that's, why it stopped, conceptually, one of the reasons that it stopped there. So then you can, of course, do the savings comparison. You can see the breakdown. You can get all the analytics out of the model. You can show, what does the cycling look like? We haven't talked about that, but that's something that you should want to factor in so that you can think about what the lifetime of the battery is going to look like. Be able to factor that in terms of degradation and, whether this is, what the use of the battery looks like. So then you say, well, you can add solar plus storage to this. You can add solar to it, of course. How does that factor in? Well, now you've got solar that's operating through much of that peak period. It's providing that energy to be able to, it's providing a lot of that energy in that region that the battery didn't have to do. And so storage is very complementary. They say it's synergistic with solar because, like I mentioned earlier, batteries like those peaky load profiles. They like that jaggedness. Well, guess what? That solar will create some of that jaggedness for you because every time that cloud goes over, that you get some sort of dip like that. And that's where that battery can smooth out those peaks and pull down, whereas solar was getting a little bit of demand charge reduction before. Now you add the battery to it and it can smooth that out and it can increase the amount of that peak shaving without having to add significant sized energy capacity to it. So to go back to some of those takeaways as I wrap up, what we had in this presentation is to remember to think about power and energy when talking about batteries. And I really can't emphasize that enough, is that when you read about batteries and you read about in your trade journals that, so-and-so utility did this size of battery, think about, well, what was the application and what was both the power and the energy that was required to do it? What size battery did they put in? I think we've mentioned several times that batteries like high demand charges and they like peaky load profiles. Solar will help you make that peaky load profile, and that's what makes the complementary aspect between solar and storage. Not only is battery sizing important, but dispatching is critically important in terms of optimizing that and optimizing your economics that can make or break a project. And finally, it's a fascinating time in the field of energy. I promise you all that when we look back on this in 5 or 10 or 20 years, the things that we were doing now, you're going to be amazed at the different, where we were and the tools that we were developing to be able to think about these projects.
Thank you, Travis. We have a few minutes for Q&A, and if we go over 1 o'clock, that's okay too. We got a little bit of a late start due to technical difficulties, but so feel free to type your questions into the Q&A function there at the bottom of your screen, or you can chat them into the chat function also. I know, Mike, you had a question about peak shaving, so if you could just repeat that question. I didn't quite understand the context when you fired that off. But Travis, let's talk a little bit about the Midwest market and some other things like resiliency. You've talked a lot about grid services, which is very important, and thank you for such a deep dive. But one of the challenges we face is that demand charges are very low here in the Midwest. And so we're always looking for other value stacks to make batteries pencil or make them economical. I'll give you an example. If a factory needs ride-through power, the ability to ride through during a brownout or blackout and avoid an uncontrolled shutdown, that can be worth a lot of money for a manufacturer. And that's often the case where we really get traction with lithium-ion storage, because that's now a viable solution for short-term ride-through, on the order of 30 minutes to an hour. Resiliency obviously is another value stack which we don't necessarily appreciate a whole lot. Outages are fairly rare. When they do happen, of course, because of some natural, storm event or catastrophe, then the grid is sorely missed. Talk a little bit about resiliency, and does Red Cloud allow you to model resiliency?
Yeah, those are definitely good. It's good questions, Tim, and we do a lot with resiliency. The challenge is, to be perfectly honest, is valuing it. And so you really hit the nail on the head with the customers that it is very important to. The ones that can tell you what an hour of downtime for their facility is worth are the ones that are very well positioned to be able to do some either resiliency from batteries or solar plus storage, and possibly even adding those to their existing firm generation. And so if you can value if you know what the resiliency is worth to you, you know very well what you're willing to pay for solutions that will provide it. And so that's kind of the key. I think that how we like to think about it is doing the modeling of what solar plus storage will add when you do those when you add it to, say, diesel generation. And so like diesel generation, oftentimes if it's a backup facility, backup power at a facility, you might say, well, I have 3 hours I want to have, or 3 days, I have a finite capacity tank, and I'm going to have a certain amount of fuel on site that will ride me through that type of that duration of outage. But of course, you could have an outage that's longer than that. And so then solar plus storage could bring that incremental resiliency and say, well, I'm going to either make this, I'm going to need to run the generator less, or I'm going to run it at a lower load. And so by doing that, if I had 3 days or 3 hours of fuel before, maybe I'm going to be able to double that. And so maybe now I'm going to have, say, 6 days of fuel if I'm at an assisted care facility, or something like that. And so if a hurricane hits, or I suppose in Illinois, a blizzard, suddenly now that your fuel supply lines become endangered, maybe now you have a longer period of resiliency.
Great. We have a question from Mehul. Does the battery cost of $300 a kWh and $800 per kW include inverters and control and monitoring components? I guess he's referring to one of your slides.
Yeah, for sure. So that's always a good, we can usually get some questions off of that slide. And so, so it's designed to include the bidirectional inverter and the fixed, in some the switch gear, for example, that you're going to put at a site. And so, that's kind of what you should have in your per kilowatt number. So you should be costing the inverter on that per kilowatt number largely, and the batteries on the per kilowatt hour number. So then the controller is kind of the wild card in terms of what that's going to cost. And so if you get big enough, the controller it can be somewhat negligible. It gets, it's in the noise. And but it can be a challenge on the smaller systems because the controller may not scale down. And so there's a variety in terms of cost. And so there are different solutions out there, and there's more coming all the time that I think are going to be able to, that you can, like we are, for example, working with a hardware partner that can integrate some of that control capability to be able to do behind the meter peak shaving into their smart inverters, such that you don't have a separate controller. And so, being able to do that then allows you to, use that type of, those costs, roughly those cost numbers that we have there without adding a separate controller. But, one way or the other, you obviously need to see the entire system cost.
Cool. Mike has a question. Early in the presentation, you referenced the conversation that you and I had about the difference between peak shaving and other services that the battery provides. One of those services had demand in the name, but it wasn't demand charge reduction. Let's just quickly review that value stack that you were referring to.
Should we go back to that slide?
Yeah, let's do that.
Okay, great.
I think you just passed it.
Yeah, I think it's right there.
Yep.
So what was the question here? It was
actually, if you go to the next slide, right here. So we've got arbitrage, frequency regulation, demand response, and peak shaving. Can you quickly differentiate those services?
Sure. So if we, so why don't we can use the ones that are, in the stack up there. So ancillary services are usually so frequency regulation is usually the one that's most common in that regard. But that's also going to include, it could include capacity. It could include black start, that different ISOs allow you to bid to provide that. So basically, these are services that are getting provided to the grid in general. Going across then, grid infrastructure, congestion relief. So there's peak shaving that is done from a utility perspective, that certain feeders get overloaded, and so being able to reduce the load on some of those particular feeders, definitely has value. And so that's ones that are it can be difficult to see from a particular project that you need to work with the utility in order to capture some of that revenue. That there's value to them for you doing this, but there's not necessarily a market to monetize it, if that makes sense. So reliability and resiliency, we've talked about, what you can do in terms of, backup power. There's also value to the utility from this respect. They have their CAFE and SAFE, I think, numbers that show the outage frequency and duration. And so they have metrics that they need to hit in terms of providing resiliency, having outages. And so, you'll see, I think there's some projects up in Washington State, for example, that they've done battery projects and positioned them such that, communities at the end of long feeders that have been prone to outages are no longer, have some backup capabilities there. And so, there's the line between, well, what's a front of the meter project and a behind the meter project. And, today those lines are pretty solid. And I think that you're going to see more of that blurring in the future. And then demand charge reduction we mentioned, and energy time shifting, is pure energy arbitrage is relatively rarer in the US. And the reason for that is you need to have a large dynamic range between basically it's your bid-ask spread, to put another way. So what is your electricity cost at night versus during the day? And if you have that, you obviously need it to be large, right? Because you're losing some energy straight off the bat through a round trip efficiency of the battery. But then you're introducing wear and tear on the battery. Every cycle costs you wear and tear, which shortens the life of the battery. And so you need to have this, as some multiple. And in the US, we often don't have that big a multiple. Whereas in Australia, I believe that they have, this could actually get fairly large. And so, certain parts of the world have more opportunity for pure arbitrage. Here in the US, I think it's more about like shifting your solar, for example. You could say, well, I'm producing solar in the morning, and I have, my part peak rate, as you saw there in SCE, was, say 6 cents. And maybe I don't have, or maybe I have an export rate that's even lower, so I'm going to shift that, into the afternoon. And so usually I think in the US we're seeing that, energy time shifting, arbitrage is combined with, something else you were going to be doing like peak shaving. And so it makes sense, it's part of the stack. It's just, and kind of the point is you're probably not doing, you're not doing it by itself exclusively.
And to Mike's question, we were differentiating peak shaving from demand response. And as I understand it, peak shaving is like capacity charge reduction or demand charge reduction. So when we're having peak load days, we're doing something explicit with the battery and other aspects of the facility to reduce our demand to the grid. And then demand response is specifically a program that utilities have, like ComEd does have a demand response program where you agree to offer some service like generator services to your facility to reduce the load that the facility presents to the grid, and the utility will pay you for whatever time slot you provide services. Is that relatively accurate?
That's right. Yep. That's it's the peak shaving you're doing because it's your bill and it's savings. I usually say that peak shaving, things you do on your bill, you don't really face competition for. It's your bill, you own it. No one else is coming to pay you, is going to pay your bill. And so whatever your load profile looks like, you have the opportunity to reduce those charges on your bill. And so when it's demand response, it's the utility paying you, saying, hey, I will pay you this if you can, reduce your load during that period. And it's voluntary, and it turns out to be it's a payment. And so really, you're in a great position if your peak happens to coincide with when that demand response event was going to occur, because then you can do what you were going to do anyway for your own peak shaving and simultaneously get paid for reducing your load through some sort of demand response program that your utility offers.
Great. There's a question from Steve about the presentation. Will we make it available? And the answer is yes. We always post the slides and the recording at cecco.com, cecco.com/solar webinar. So that's the landing page for the webinar. We will post the slides there. And then, here at Continental, we do work with batteries. We've installed, a few more than half a dozen projects, and it's a variety of reasons, but frequency regulation is the most common service that batteries are providing, kind of a revenue generating service. And then ride through is another key service. And we didn't necessarily talk about this, but when you combine solar and storage, you can take the investment tax credit, which is currently a 30% tax credit on that storage equipment. So that is definitely something to look into. If you're investing in solar, you should look into investing in solar and storage, which basically you're expanding the capabilities of the solar array by pairing it with a battery storage system, and then also taking some tax benefits. Travis, tell us a little bit about how people can get a hold of you and how you work.
Sure, yeah. So I would encourage you to visit our website, muGrid.com. We're also on LinkedIn and Twitter, and you can find us there as well. We get involved in a variety of projects. We're often on a project basis that we're brought in for our modeling expertise. Right through to preliminary design. We also do some performance monitoring to be able to, that's the beauty of a battery, is that, even once it's in the ground, you can still, you can improve your economics by improving your dispatching. So, it's something that is you should, you want to continually think about as you're doing. And so, so we're happy to talk about, solar projects, storage. We do lots of storage projects. Really, sort of any energy, that's, the tough questions, revolving around energy, we're happy to engage with and, see how we can help out.
Can you forward to the next slide, and I'll make a few announcements of upcoming events? Sorry, to the second to last slide. So I think we'll wrap it up there. Thank you so much, Travis. Again, people can get the slides on the Continental website. We do have a couple of upcoming events that we'd like you to know about. Solar Power Midwest is coming up in just 2 weeks in Chicago. That's November 13 to 15. The main event is the 14th and 15th. Please do reach out to me if you'd like to get a pass to the trade show. We do have a number of free passes to the trade show where you can visit with manufacturers, service providers, installers like ourselves. We will have a booth, and other organizations in the renewable energy industry. So that's a great event, 3-day event. On the 13th, there's a number of pre-con events. So check out, if you just Google Solar Power Midwest, or if you follow the link on the posted slide, you'll find that. This Thursday, we do have our Chicago Solar and Storage Meetup at Continental in Oak Brook. We meet the first Thursday of the month at Continental, and this week we will be discussing solar and storage and recapping Travis's presentation, as well as doing a rooftop tour of our 55 kW rooftop array at Continental. And then finally, SolarWorks for Illinois is a monthly webinar. We give a webinar on the last Tuesday of the month, so the next one is November 27th. And that is going to be intelligent monitoring systems for solar projects and portfolios with Anson Moran, who is the CEO of Meteo Control North America. And Meteo Control is a leader in the monitoring of renewable energy assets industry. So we're excited to have Anson on the show. Thank you all for joining us, and we look forward to seeing you on future webinars. Again, thank you so much, Travis, for being our speaker today. Really appreciate it.
Thank you very much, Tim. It's been a pleasure.
All right, you take care. Bye, everybody.